Say we have a directed graph that looks like this, and then the corresponding adjacency matrix representation will look like this. Now we'll need to have a convention of left to right here. So let's say that each row represents I and each column represents a j, such that if we have a number that represents an arrow from I to j, so say this row represents vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, and this is for vertex 1, 2, 3, 4, 5. Now this number 0 represents that there is the cost of going from I to j. There's a path and the cost is 0. There's an edge from 1 to 2 with a cost of 3. That's what we have here. There's an edge from 1 to 3 with a cost of 8. 1 to 3 with a cost of 8. There's an edge from 1 to 4 with a cost of infinite. That means there's no edge from 1 to 4. And there's an edge from 1 to 5 with a cost of minus 5. So 1 to 5 with a cost of, minus 4. So here's the adjacency matrix representation of this matrix, and we can also call this the weight matrix, weight of this graph. So if this is G, then the corresponding weight matrix W is given by this 2D array. The idea behind using dynamic programming to calculate all pair source path distance is to use something known as a matrix L at various indices. Now, at various indices, what this matrix conceptually represents is the all pair distance between all of these vertices. So here once again we have 1, 2, 3, 4, 5. These are the 5 vertices, 1, 2, 3, 4, and 5. What this matrix represents is the shortest path between all of these pairwise vertices with maximum these many number of paths. So if we allow shortest paths to have maximum 1 edges, so this 1 means maximum 1 edge, what will be the shortest paths between all of the pair of vertices? So if we allow only 1 edge between all the pairs of vertices, obviously the shortest path will be the weight matrix itself. So for that reason, L1 is the weight matrix itself. Now the idea behind using dynamic programming is to grow this L matrix, this minimum weight matrix, step by step. So we calculate L1 and then we calculate L2, L3, and so on. So here's the algorithm. It takes your current weight L matrix, which initially will be W, and then also takes your weight matrix. So we set the number of rows and columns, or n equals the number of rows or columns, and then we create a new matrix and we fill it up with infinite. So this is redundant here. Once we fill that a new matrix with all infinite values, we're good. Then we simply iterate over all possible values in this matrix, so all rows and all columns. And then for each value, what we check is, what we would like to compute is the minimum of what we already have, plus the minimum of going to ith node, and then the weight of that ith node, or say kth node, to j. So we'll look at an example as well. So what the extend shortest path method does is it takes, say, L1 as input and gives you L2. If it takes L3, it gives you L4, and so on. Once you compute Lm, which is the number of vertices, you are done. And actually, even if you compute Lm plus 1 or as many times more, you'll still get the same value, because once you have found the shortest path, this doesn't further change anything. So to demonstrate the example of how to grow this L matrix, or say for example from L1 to L2, let's take an example. Say we are interested to calculate L2 from L1. So once again, let's create this matrix. I have my rows 1, 2, 3, 4, 5, and then my columns 1, 2, 3, 4, 5. So let's start with the first index. So now we are inside this for loop. What we want to check is there a path at least that goes through one extra edge from 1 to 1? So let's see if it's shorter. So the minimum cost we have from 1 to 1 is currently 0. If I go via 2, so the cost of going from 1 to 2 is 3. And then let's look at the cost of going from 2 to 1. So the cost of going from 1 to 2 is 3, and then the cost of going from 2 to 1 is infinite. So infinite plus 3 becomes infinite, so that's not the minimum. So I'm going to maintain my 0. The cost of going from 1 to 3 is 8, and then the cost of going from 3 to 1 is infinite. So that is still is higher, so I maintain my 0. The cost of going from 1 to 4 is already infinite, and the cost of going from 4 to 1 is 2. Infinite plus 2 becomes infinite, so it's even higher than 0, so I keep my 0. The cost of going from 1 to 5 is minus 4, but then the cost of going from 5 to 1 is infinite. So infinite plus minus 4 is infinite, so I maintain my 0. So the cost of going from 1 to 1 itself, the minimum cost with maximum 2 edges so far is 0. Now the current cost of going from 1 to 2 is infinite because that's where we initialize the L matrix. And then we check if I went to 2 via 1 itself, so the cost of going from 1 to 1 is 0, and then the cost of going from 1 to 2 is 3. So 3 plus 0 is 3, so this is better, so my new cost is 3. And let's see if I can go to 2 via 3. So the cost of going from 1 to 3 is 8, and then the cost of going from 3 to 1 is infinite. So this is very high, so I still maintain my 3. Next, the cost of going from 1 to 4 is infinite. This is already higher, so I drop it. The cost of going from 1 to 5 is minus 4. This could be better. And then from 5 to 2 is actually infinite. So infinite plus minus 4 is infinite, so I still drop this, so I maintain my 3. Similarly, my cost of going to 3 also maintains at 3. Let's see if we can update the shortest path from 1 to 4. So the current value that we have is infinite, that is the beginning. So let's see, if I go from 1 to 1, and then from 1 to 4, if that improves the cost. So from 1 to 1 is 0, and from 1 to 4 is infinite, so this doesn't change anything. 1 to 2 is 3, and from 3 to 4, so 1 to 2 is 3, and from 3 to 4 is also infinite, so this also doesn't change anything. And from 1 to 5 it's minus 4, and from 5 to 4 it's 6. So 1 to 5 minus 4 and 5 to 4 6. Summing these we get 6 minus 4 is 2, and since 2 is better than infinite, we replace with 2. Similarly, the cost of going to 5 doesn't change, it maintains at minus 4. Let's look at the next one. So this was for the first row, first vertex 1. Let's calculate for the second one. So let's look at the cost of going from 2 to 1. The cost of going from 2 to 1 itself is infinite. Let's say I plan to go to 2 to 1 via 2 itself. So the cost of going from 2 to 2 is 0, and then from 2 to 1 is still infinite, so that also doesn't change anything. The cost of going from 2 to 3 is still infinite, so that also doesn't change anything. So even via 3 is not a good idea. Let's try the cost of going from 2 to 4, 2 to 1 via 4. So if I go to 4 from 2, the cost is 1. And let's say from 4, if I go to 1, then the cost is 2. So 2 plus 1 becomes 3. This is better, so we can replace this with a 3. And then let's try the last one. The cost of going from 2 to 5 is 7, and then from 5 to 1 is infinite. So this is still infinite, so this maintains at 3. So in this way, I can fill up the L2 matrix, and similarly next calculate L3 and so on. In this way, if I calculate up to L4, then I'll get my solution. I was always referring to L1 because L1 and W are same. But for calculating L3 and future L matrices, if you look at this term here that calculates the minimum, we actually have to use one of the summing terms from the weight matrix and the one from the previous L matrix. So I was referring to L1 all the time, but for subsequent calculations of L3, you'll have to refer to the weight matrix and the L matrix.